This video is for determining subatomic particles in an atom. So you've already learned what subatomic particles are, and those are protons, neutrons, and electrons. Now you're going to figure out how to find the numbers of protons, neutrons, and electrons in an atom. And so we're going to start with that. First, let's review what's in an atom. In an atom, we have those subatomic particles. We have protons and neutrons, and those are inside the nucleus. And then we have the electrons, which are outside the nucleus, moving around in a circular path in an electron cloud or on the energy levels or energy shells. So we have three types of particles that we're going to be looking to find today. So we're going to start with a couple of guidelines. It says to determine the number of protons, neutrons, and electrons in an atom, we need to follow these steps. So the first thing you need to do is find the atomic number and the atomic mass of the element that you're trying to get the information from. So you're going to use your periodic table to do that. So in this picture you can see the example is carbon. So the first thing you would do is, if you're looking to find these values for carbon, find carbon on your periodic table. And when you do, you should find a square with a symbol that looks something like this. And you see the square on the periodic table, you'll find carbon, and you'll see that these squares on the periodic table have an atomic number, the element symbol, the element name, and the atomic mass. You're going to need all of this information to help find your number of protons, neutrons, and electrons. So we'll start there. We'll start by finding the symbol on the periodic table. Okay, next what we're going to do is, once we've found that symbol on the periodic table, we're going to use that information and we're going to plug it into the letters APEman. APEman stands for something. Each letter in APEman means something different, and they're all going to help you to find the values that you need. So let's start with the word ape, A-P-E. In ape, the A stands for atomic number. And if you take a look, the atomic number is found right here on your periodic table square. The P stands for number of protons, and the E in ape stands for the number of electrons. So the saying for ape is that ape is equal. A equals P equals E, which you can see right here. That means that all of those values are going to be exactly the same. And our atomic number, we know, is found right here. It's given to us on the periodic table. So we don't need to do anything to figure that out except look. So if we know that carbon's atomic number is 6, and A equals P equals E, then that means that carbon has 6 protons and 6 electrons, because all of those values have to be the same thing. So we've already found protons and electrons for carbon, simply by just looking at this number right here. That's all we had to do. Now here comes the next part, and the next part spells man, M-A-N. And again, those all stand for something. M equals mass number, which is right here. A is atomic number, same as it was over here. And N means the number of neutrons, which is the last thing that we're trying to find. So what's going to happen is man says M minus A equals N. That's how you're going to find your neutrons. The mass number minus the atomic number gives you the number of neutrons. So if M is our mass number, and our mass number is 12, A is our atomic number, and our atomic number is 6. And we subtract that, 12 minus 6. Then 12 minus 6 equals 6, and carbon has 6 neutrons. So again, just taking the values that we found in our periodic table square, we are able to find out the number of protons, neutrons, and electrons just by plugging them in to the words APEman. The other thing to remember is in a neutral atom, and a neutral atom means that it has no charge, which is most of the atoms we're going to be dealing with in 8th grade. So in a neutral atom, the number of protons and electrons will always be equal, because if you think about it, protons are positive and electrons are negative. And if you have the same amount of each, those protons and electrons, positives and negatives, those charges need to cancel each other out in order to make it have no charge or be neutral. So that's why A equals P equals E. The protons and electrons have to be the same number. So we're going to practice. I walked you through how 8-man works, but sometimes it's better when you do your own. So here's a hint too before we start. It says, remember, always round the atomic mass to the nearest whole number. No decimals. So for example, if your atomic mass, which is the bottom number, is 15.999, we don't want that decimal there. So we're going to round it to the nearest whole number, and that's going to round up to 16, and that's the number you would use. So let's move on. Let's try an example. Here's hydrogen. This is how it looks on the periodic table. And we're going to find the number of protons, neutrons, and electrons in an atom of hydrogen. And we're going to do that by using 8-man. So 8-man is here. It's down below to remind you. A equals P equals E, and M minus A equals N. So I want you to put this in your notebook and write it down and go through it with me as I do it so we can figure out the number of subatomic particles that hydrogen has. So let's start. Let's start with A equals P equals E. A is the atomic number, which is right here. And the atomic number is 1. So that tells us that hydrogen has 1 proton and 1 electron. So far, we've got 2/3 of it finished. The last part is M minus A equals N. The atomic mass minus the atomic number will give us the number of neutrons. So remember what we said about the mass. You always need to round it to the nearest whole number. And in this case, the nearest whole number is 1. So if we take the mass minus the atomic number, 1 minus 1, that gives us 0. So now we have all of them done. We have the ape and the man, and we have our protons, electrons, and neutrons finished. So A equals P equals E is the value of 1. 1 proton, 1 electron. M minus A equals N gives us 1 minus 1 equals 0. Hydrogen is an exception. Hydrogen is an element that has 0 neutrons. Now, you're not going to find that with any other element, but hydrogen is a special one. So hydrogen has no neutrons. And so we've just done 8-man for hydrogen and figured out its number of subatomic particles. So now that we've done a few, I want you to try some on your own. Write these in your science binder. Go through and write the abbreviations for 8-man and what it means. And I want you to find the number of subatomic particles, or protons, neutrons, and electrons, for each of these elements on the periodic table. And just remember, use 8-man. So the first example here is aluminum. Pay attention to its atomic number and atomic mass. And number 2 is argon. Again, also pay attention to the values that you're going to need. Plug them in and write down how many protons, how many neutrons, and how many electrons both of those elements have. When you're done, you can share with your class or your teacher, however you're going to do it, and then we're going to move on from there. Okay, before we move on, I'm just going to give you the answers very quickly because hopefully you already discussed them as a class. For aluminum, you should have found that aluminum has 13 protons, 13 electrons, because that's ape and they're equal, and it has, after you subtracted correctly, 14 neutrons. For number 2, with argon, argon has 18 protons, 18 electrons, And then again, after subtracting, and make sure you rounded that decimal correctly, you should have gotten 22 neutrons because it should be 40 minus 18. Next, okay, now that you know 8-man, and I'm sure you rock at it, you might be wondering why you need to know that. Why do I need to do 8-man? Why do I need to figure out the protons, neutrons, and electrons? Well, we're going to move forward. Knowing the number of subatomic particles helps us so that we can draw a Bohr model. A Bohr model is what you normally see when we show you what an atom looks like. Every element has its own original Bohr model, and this was invented by a man named Niels Bohr, as you can see up in the picture. He wanted to show the atomic structure, okay, because atoms are very, very small. We can't see them without a microscope, and we don't have microscopes of that capacity here. So he came up with the Bohr model, and so we are going to draw Bohr models to represent what each atom looks like. And remember, each atom is different because they all have different numbers of subatomic particles. So we're going to start. We always start with something that looks like these empty rings, and these empty rings are going to be where you put your electrons. Remember that electrons are the particles that move around the outside, and the nucleus that you see right here is what's in the center. And hopefully we all remember what goes in the nucleus, and those are the protons and the neutrons. So we usually start with something that looks like this, and then we need to take, and after we do 8-man, put the subatomic particles where they belong in order to form a model of that atom. So the first example we're going to look at here is carbon, because I did that example before, and we've already done 8-man for it. So if you look back in your notes, or you want to go back in the slides, you can see that carbon has 6 protons, 6 neutrons, and 6 electrons. Okay, and remember we did 8-man for this one as an example, so it's already done. But the atomic number 6 tells us the protons and electrons, and then when we subtract the mass minus the atomic number, it gives us the neutrons. So for carbon in this case, it's 6 of everything. So what we need to do is we know that our protons and our neutrons go in the nucleus, and protons I'm going to make red because we normally make them red. Neutrons I'm going to make blue, and electrons I'm going to make green. So let's start. Let's take our red, and again protons go in the nucleus, which is the very center, and I'm just going to make 6 dots. 1, 2, 3, 4, 5, 6. So we have now put our 6 protons for carbon inside of the nucleus where they belong. 6 positive charges in the center. And if we look next, 6 neutrons. So I'm going to take my blue. We know that neutrons also belong in the nucleus with the protons. So you can put them in there. You can mix them up. 1, 2, 3, 4, 5, and 6. So same thing, 6 neutrons in the nucleus. They have neutral or no charge, and our nucleus is now done. And I'm just going to mark that they go in the nucleus. And last, we are going to go to our electrons, which are last. Now, electrons are a little bit trickier. You can't just throw them wherever you want. Remember, electrons go on the energy shells. But with the energy shells, there are some rules that have to be followed. As you can see, there are 3 energy shells that I have placed on this blank model. Now, we only go up to 3 energy shells in 8th grade. Depending on the atom model or the Bohr model that you're making, you might not need all 3. So I think in this case we're not, but I'm still going to teach you the rules for your electron configuration. Electron configuration just means how the electrons are placed. So we're going to start. Carbon has 6 electrons, so we need to put them where they belong. So the rules here for your energy shells or energy levels is that on the first energy level, you can only hold 2 electrons. That's the maximum. Okay, you can have less, but you cannot have more. And you need to start at this first energy level and work your way out. Okay, you cannot just go wherever you want. So starting with this very inside energy level, or the first energy level, I'm going to take and I'm going to put 2 of the 6 electrons. Okay, now I understand that we still have more. We have 4 left that we need to put in order to make 6. But for now, this first energy level can only hold 2, so I need to stop. Then we're going to move outward to the next energy level. This is the second energy level, or the middle one that we're looking at. There is a rule for this one too, and this energy level can only hold 8. Again, it can hold less, but it cannot hold more. And you can only move to this energy level if the first one has been filled. Think of it as seats at a lunch table. Everyone's moving in, with their lunches, and you fill one lunch table before you go on to the next. Or rows in a movie theater. You fill in one row before you start going to the next. So the second energy level can hold 8, and we're going to fill in the rest of our needed electrons for carbon. We have 2 here, so we're going to keep counting. 3, 4, 5, 6. Okay, and that's 6. Carbon only has 6. So we have 6 total. We have 2 on the first energy level and 4 on the second. So did we fill it? No, we don't need to fill it. That's okay. It can hold up to 8, but we just don't need it. I'm going to move to the third energy level and explain the rule for that one, and the rule is actually the same as the second. The third energy level can also only hold 8 electrons. It can hold less, it cannot hold more. So again, if you're dealing with a larger atom model, you might have to use all 3 energy levels. In this case, we did not use it, so in fact, it doesn't even need to be here for this particular model. But this is what a Bohr model of carbon looks like. You have your protons and neutrons in the center, and you have your electrons placed according to the capacity rules going around the outside. So what we're going to do is we're going to keep practicing. The next example is oxygen. So in order to draw a Bohr model of oxygen, the first thing you need to do is ape-man. You do ape-man, again, to figure out how many protons, neutrons, and electrons you have, and then you use those values to go ahead and draw. So you might want to pause the video and do ape-man, and then come back, and I will do that all with you and show you the example. Okay, so if you looked at the periodic table square for oxygen, okay, you have your atomic number at the top, you have your atomic mass at the bottom. You're going to use that and plug it in to ape-man to find your protons, neutrons, and electrons. So I've done it down below, and hopefully you have it too. A equals P equals E. So the protons and electrons are all equal to this number right here. So oxygen has 8 protons and 8 electrons. So I'm going to put the symbols right here. 8 protons and 8 electrons. And then for neutrons, we have done M minus A equals N. So the mass minus the atomic number is 16 minus 8 equals 8. So again, we found another atom where all the values are the same number, 8, 8, and 8. And that's okay, but just remember that's not going to happen all the time. So we've done ape-man. Now it's our job to draw the Bohr model of oxygen. So again, remember that protons and neutrons will go in the center in the nucleus. So I want you to go ahead and draw that, and then come back and I'll have it done. So here is your nucleus for oxygen. Again, your dots don't all have to be in perfect rows. The protons and the neutrons can be mixed together because that's how it is normally. I just put mine there so you can see that there are 8 of each, the reds and the blues, the protons and the neutrons. But now we're going to do electrons, and again, remember electrons have rules. We have 8 electrons. We can only fit 2 of those 8 on the first energy shell, the closest one to the nucleus. So I'm going to put 2. Now we have 6 left over. And if you remember, this second energy level can hold 8, and we only need to place 6 there. So I'm going to put 6. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 total. We followed the configuration rules, and this is what a Bohr model of oxygen looks like. Here's another example. This is sodium. So go ahead and do the same thing, do ape man, and then continue and draw your Bohr model using those values. So if you went through and you calculated ape man, you should have found that sodium has 11 protons, 11 electrons. Remember, they have to be the same because this value is positive. These are negative, and they need to have the same amount to cancel each other out and make a neutral atom. And then if you subtract properly, you should have come up with 12 neutrons for sodium. And here's the Bohr model for sodium. And I made it a little bit neater so you could see because there's a lot more subatomic particles. Sodium is a larger atom. But in the nucleus, we have our protons and neutrons, the red and blue, 11 protons and 12 neutrons. And then the greens are the electrons on the energy levels. So since this is larger, we're using all of the energy levels this time. We have 2 on the first energy level because that's all it can hold. We have 8 on the second energy level, okay, which makes 10, but we need 11 electrons. Okay, so we actually have one more, so that one lonely electron is going to go on the third energy level because the second energy level is filled to capacity. So we have 2 on the first, 8 on the second, and 1 on the third, making it a total of 11 electrons. The next example is going to be much smaller. It's helium. So again, figure out ape man, go ahead and then use those values to draw the Bohr model for helium. Okay, and you should have came up with this. Again, very simple. 2 protons and 2 electrons. And then when you subtract, 2 neutrons. So again, helium is one of those that has all the same values, 2, 2, and 2. And now after you've done ape man, you need to take those values and use it to draw your Bohr model. So again, your red and blue, your protons and neutrons need to go inside the nucleus and go ahead and draw them. And then your 2 electrons, your green, need to go outside on the energy levels, starting with the inside energy level, your first one. And there's only 2, and the first one can only hold 2, so that's all you need. So in this case, we wouldn't even need to show these other energy levels. If you're not using them, then don't include them in the picture. Okay, so helium, again, is a very small atom. Its atomic number is 2. It's way at the beginning of the periodic table, so it's not going to be a very large atom. It's not going to have a very large Bohr model. So you've practiced several. You know ape man, you know how it relates to drawing a Bohr model, but if you need more practice, okay, you're going to go over it in class on your own. This will be posted on YouTube if you need some more practice. But again, I think that this was a really great review. I think you really know how to draw Bohr models, and we're going to practice coming up, and we're going to move on into some other topics. So just work on memorizing ape man so that you can use it when you need it down the road. Okay, because ape man is very important to helping you remember what we've been working on today.